So back to tides, we were talking about the tidal bulge. Again, the tidal bulge is the water here that's being pulled away from our planet. Remember that the tides are due to the gravitational pull of the moon and the sun. So that force mostly acts on the water of our planet. So it pulls the water. You can see it creates this tidal bulge. Again, that's due to the gravitational pull of the moon and the sun. So if we look at this diagram here, you can see that we actually have two tidal bulges. We have the lunar tidal bulge, which is due to the gravitational pull of the moon. And then we have the solar tidal bulge, which is due to the gravitational pull of the sun. You can see that the solar one is smaller because it has less of an impact. Again, the moon's closer, it has a stronger gravitational pull. So the lunar tidal bulge is going to be larger because the moon has a more impact on our tides. Notice that the solar tidal bulge is pointed towards the sun, and then the lunar tidal bulge is pointed towards the moon. So the lunar tidal bulge rotates as the moon rotates around our planet, and then the solar tidal bulge is always pointed towards the sun. So it's really the movement of the lunar tidal bulge that gives us our tides. Again, it's the movement of the moon that really causes our tides. So if we look at our tidal bulge, again, this is what we call an idealized tidal bulge, which means that it's not what we see in reality. Notice here that our planet's straight up and down. Remember that that's not actually the case due to the collision that formed our moon, that collision with Theos very early on in our existence that tilted our planet. And so because we are on a tilt, we do not actually see this idealized tidal bulge. Instead, we are on a tilted axis. So we call that declination. You can see here that those different latitude lines are going to experience different tides. Notice here that the tidal bulge, again, is not perfectly aligned with our planet because of that axial tilt. So this diagram's in your book as well. It's showing you the declination or the angle of that tidal bulge as the planet rotates. So that tidal bulge is following the moon around. It takes 28 days for the moon to go completely around our planet. And then our planet rotates it rotates every 24 hours. So our planet's continually trying to keep up with that tidal bulge. It's continually rotating within that bulge. It's the rotation of the planet that really causes our tides. Again, that bulge follows around the moon. As our planet rotates, it rotates throughout that bulge. So it's the Earth's rotation that really causes the tide changes. Because we're rotating within that tidal bulge. So different parts of the planet experience different tides at different times because partially due to the tilt of our planet. You can see here that the northern hemisphere is experiencing this tidal bulge while the other side of the planet is also experiencing that. So again, that's not evenly distributed because we are tilted. We also have continents on our planet. So this isn't exactly what we see either. Continents create friction. So tides are very complicated due to the declination and the differences between alignment and the moon and the sun and very regional geographical differences. We see a lot of different tides. Those can be graphed or maps. You guys saw this as well in your textbook and in your lab. So we have this map here that looks at cotidal lines and amphidromic points. Amphidromic points are areas where we see zero tidal range, which means that the tide is the same throughout the entire day. That's due to the geography of the area and also its location on the planet itself. So those amphidromic points are, again, areas where we see no tidal ranges at all. And then these cotidal lines, these colored lines represent areas of high tide. So this line here, this 12-hour delay, this 10-hour delay here means that it takes us 10 hours to rotate into that tidal bulge. So we see very large tidal ranges in those areas with higher numbers, and then